Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about the pressure distribution on an airfoil, and further we will discuss about airfoil nomenclature and airfoil characteristics. So, in the previous lecture, we had discussed about the concept of center of pressure, and we also discussed about the geometry of an airfoil. So, we very importantly introduce the concept of camber. So, we will revisit that concept once again, and we will now introduce the concept of symmetric airfoil in addition to the cambered airfoil that we already looked at. And then we will see how the pressure distribution on these airfoils would look like when the angle of attack is 0 or otherwise. Now, in symmetric airfoil, the camber line superposes on the chord line. That means, you essentially do not have any camber, and therefore, when you equally distribute the thickness about the camber line, which is nothing but the chord line, the thickness is symmetrically disposed about the chord line. So, this is like a uniform flow approaching a symmetric airfoil, and you can now understand that to the flow this geometry will look absolutely symmetric about the chord, and therefore, the streamline pattern will be identical above and below, or rather kind of mirror images, and that would end up producing identical pressures on the upper and lower surface corresponding to a particular x by c. What that means is that you do not have a pressure imbalance between the upper and lower surfaces of the airfoil, and this consequently would mean that this will end up producing a net 0 lift. On the other hand, in the case of a cambered airfoil, of course, we know that there is a non-zero camber, and then once you distribute the thickness above and below the camber line, you end up getting the airfoil shape, and the shape certainly looks asymmetric about the chord, and that is how it is visible to the flow as well, and therefore, when the flow moves around this surface, the streamlines are asymmetric. Consequently, the pressure distribution is also unequal on the upper and lower surfaces at any given x by c. If you take care of this pressure imbalance, which is largely the variable which influences lift, the lift becomes non-zero even at an angle of attack of 0 degrees. So, at an angle of attack of 0 degrees, lift is 0 for a symmetric airfoil, while lift is positive for a positive cambered airfoil. What we mean by positive cambered airfoil is that the camber line is above the chord line. If incidentally the camber line was below the chord line, that would have led to a negative camber. For example, if this is a chord line and the camber line has moved below, this is an example of negative camber. However, we are not bothering about that, we are bothering about a positively cambered airfoil, and it ends up giving us a non-zero lift which is positive. Now, we would be interested to see, of course, how the pressure distributions really look like in principle on the upper and lower surfaces of the airfoil. One interesting thing is that if we are interested to look at the thickness of the airfoil and probably identify a location where it has maximum thickness, then it is easier done on a symmetric airfoil, because you can identify the thickness change along the length of the chord line much easily over here because of the absence of camber. So, one may say that by careful observation that this may be the location of the maximum thickness. So, wherever the highest ordinate values are obtained for the upper and lower surfaces in terms of magnitude, that is where the maximum thickness would be obtained. So, you can say that that is T max, maximum thickness. There is also a location corresponding to that. You can say x by c T max. So, that is the x by c value where the maximum thickness actually occurs. Now, as we said that we would like to have a look at the pressure distribution. Let us try to make some plots to understand how it looks like. What happens is that when the flow approaches the airfoil, when it is coming close to the leading edge at alpha equal to 0, you get a stagnation point. What does that mean? Where the local velocity becomes 0. We discussed it in the context of the pitot-static tube in a previous lecture. We had talked about a stagnation streamline and a stagnation point at the orifice, at the end of the orifice which was facing the flow directly. So, the leading edge of this airfoil has a similar stagnation point where the flow goes to a 0 velocity, and consequently the pressure coefficient, if you consider it to be defined by incompressible flow, will be given by this expression which we studied earlier, and therefore, Cp becomes equal to 1 whenever you have stagnation. So, if you are not considering viscous effects and additionally you are considering inviscid incompressible flow, then that is how it works, that the peak value of Cp will be 1. When we plot the Cp distribution, we usually plot the positive values below and the negative values above. This of course gives you the x by c side, and on the y axis we are plotting pressure. So, the leading edge is where Cp equal to 1 is obtained, and then the flow very rapidly expands or rather accelerates, and then gradually decelerates. The pressure may come down later on as it approaches the trailing edge part of the airfoil. So, this is the stagnation point where Cp has gone to a value of 1. Then there is a very rapid acceleration in this region where the flow is accelerating because of the upward sloping surface. Then it kind of gets flatter and then gradually slows down. So, depending on the shape of the airfoil, this part can take different shapes. It depends how quickly it is accelerating and then how quickly or how slowly it is decelerating.